So remember that we came up with that, well, let's start back at the beginning. Back in Calc 1, you used this expression to start with your estimates for the derivative of the function, right? So back in Calc 1, way back at the beginning when you were trying to find slopes of tangent lines, you looked at slopes of secant lines with that h changing just a little bit, let that go to 0, and that's how, with a limit, that's how we calculated a derivative, and then of course we did a bunch of rules. But generally speaking, if you've got a table of values, you can't do a derivative with rules, you have to do estimates, right? And the process that we're going to talk about today, we're going to do it for derivatives. Pardon me. We're going to do it for derivatives, but the process we're going to talk about today, you can do for any function that we're looking at that tries to estimate a quantity and then do it by smaller and smaller intervals. So for example, back in Calc 2, you talked about doing some numeric integration techniques, trapezoidal rule, Simpson's rule, those kinds of things, right? And you had the small errors that you, the small little changes in your interval to use for your delta x and those formulas. You have to use numeric integration for some functions. There's just some functions that you use that you just cannot possibly take the integral of. And you want really good estimates of the integrals relatively quickly, and for a couple of reasons. Is your chair broken? Hey. You want, for a couple of reasons, you want good approximations relatively quickly. You want good approximations because you want accuracy. You want quick approximations for computational purposes and for machine error purposes. And we're going to show an example of that here today as well. Okay. So anyway, we're going to do all of the stuff that we're going to talk about today on derivative formulas, derivative estimates, but know that the process that we're doing can be used on anything that talks about approximating something in terms of this little change that we have. So like numeric integration, for example, where if you have a function given to you, you still need to use numeric techniques to be able to approximate it. Anyway, this was our first formula that we came across back in Calc 1. We talked a little bit about this last time, that the error term is just in terms of the h, right? Whatever the h is. It was on the order of h. Notice that that the exponent here is is a 1. So we say this is an order 1 approximation of the derivative. When we're talking about the h to the power is the order that we're talking about here for the error. So this is an order 1 approximation. This is also called the forward difference formula. If I go the other way, and instead of adding an h to the x and subtract, you might be able to guess what that formula is called. It's a backward difference formula, yep. This is also O of h. Both of these are O of h. I mean, the difference between these two things is not much. It's just a matter of how you're calculating the slope, right? So again, if you think about this from a calculus perspective of what you did before, if you were trying to figure out the derivative at this x value, the forward difference just meant you added your h and found these 2 points and looked at the slope of that line, which is, you can't barely see, right? The backwards one will just see instead. We'll just subtract the h and do it that way and find that line instead. Okay. Right. At the end of class last time, we talked about a new formula that gave us a little bit better error estimates. It's a little bit there. Error. Well, whatever. Doesn't matter. A little bit error was better on the order of the error. Right? We had error that was smaller, so things should converge faster. Where you look going the f of x plus h and your f of x minus h, and then divide by 2h. We said that the error term was dominated by the h squared piece, so it's O of h squared. This would be an order 2 approximation. And again, that means that as we shrink our h, this should converge a little bit faster, hopefully, to our value for the derivative. Well, one was forward, one was backward. This one's using on both sides. What do we call this one? No, kind of that little central is what we're using. Yeah, so it'd be central difference formula. All right. And there are a bunch of different formulas that we could possibly come up with. I think they have a few in the book and the exercises, and then you look at other books and have other different other exercises. We might play around with a couple of these today. But what I'm more interested in is doing some numeric things and then talk about another formula way to get to some approximations, the extrapolation formula we're going to talk about. But let's just give a visual representation here of the difference in the errors and also why we might want things to converge a little bit faster depending on machine issues. So again, what we're talking about here when we're approximating these things is basically when we're doing these approximations, we're truncating off the error piece, right? We're just dropping the part that has the h squared, the h cubed, and so on, right? We did that in terms of a Taylor series last time, right? What we're doing is we're just dropping that off, so it truncates. So there's going to be some error anyway. And then eventually, though, you're also going to get to the point where you're dividing by very, very small numbers, which is going to make things get crazy with as far as the number goes, or as far as the machine goes. Okay, so let's just see if we can come out and just look at a specific example, a pretty easy one. So let's look at f of x equals e to the x, and let's try to estimate. Oops. F prime of 0 using a couple of these formulas. So we'll use the forward distance formula, a difference formula, and the central difference formula to estimate f prime of 0. Now, why am I doing this specific example? Well, we know what the answer to this is. Derivative of e to the x is e to the x, and then we put in 0, we get 1, right? So we know what the answer is, so we can do the errors pretty quickly, right? Okay. So let's go over to Excel real quick. Good morning to you too, Excel. All right, so let's just start with a small value of h. Let's decrease it by a power of 10 each time. So I'm going to start with an h value of 0.1, and then the next one will be 0.01, and then 0.001, and so on down the line. So let's just put the h's in there. So first one I'll put in 0.1, and then I'll just divide it by 10 each time. Oops, there we go. Divide it by 10 each time. Why are you not? What is going on with everything today? A2 divided by 10. Okay. Divided by 10 each time and copy it down a ways. What do you mean 0.01? There we go. Oh, it's a little bit better. There we go. I don't know why everything's getting crazy this morning. All right. So again here, we're just taking our steps to be really, really small. Eventually, of course, whatever precision that we have, the machine's going to turn it into the 0 anyway, right? Eventually. Okay. All right. So if we want to use our derivative estimate at 1, let's do forward difference first. So I'll just put that. I'll just use FD to label that. Our forward difference would mean we're going to do f of 0 plus h, so in this case just f of h, right? And the function is e to the x, right? So I'm going to do e to the x, e to whatever this is, minus 1, because it would be the function value at 0, right? And then divide by the h value. So what we're going to type in here. Yes. Yeah, so I typed in 0.1, and then I just divided it by 10, and then just copied it down. So I just divided it by 10 each time. All right, yep, you're welcome. So remember, in Excel and in R, if you want e to a power, we use the exp function. So in this case, I want exp of just the h, because we're doing this at 0, so I don't have to worry about adding or subtracting anything in there. E to the 0 is 1, and then we'll divide by the h value. I'll go back and get the formula back out again. Remember, the formula is f of x plus h, with the x value we're interested in is 0, right? So I don't need to put 0 plus in there. I can just put the value. E to the 0 is 1, and then we're dividing by the h. Right? Okay. We can copy this down. Notice something goofy is going on. Is it raining? Yes. Okay. Notice something you can see is already goofy going on when the numbers are starting to get small here. Right? Notice it got down to, it thinks it's really close to 1 here. It's not even displaying the decimals, and then it started displaying decimals again. So it's having some issues right away that you can see where it's the division by something really, really small is making something else going crazy with the numbers. And again, that's just due to machine representation and truncating things. Pardon me. Let's see if we can do this in terms of the error. So for the error, remember the error is just, and I'm just going to do signed error, just how far is it away from the true value. The true value we know is 1, and the approximated value is what's over in B2. So I'm just literally subtracting the 2. Okay. If I take that and copy, well, if I can copy. Now look at your errors here. And we're going to do something else with this computation in a second. But look at your errors here. We've got, notice it's 0.05, 0.005, and then I've got 10 to the negative 5th, 6th, 7th, 8th, 9th. But then the errors start going back up again, right? So something's going on with the machine representation that's making it less accurate the closer we get. So again, if this kind of maxes out in a sense, the accuracy here when we get to, what is that, 10 to the negative 8? I did my decimal point right. 3, 6, 8 places over. We kind of maxed out our accuracy somewhere around there because when we went to the next one, the error got worse. Right? So this is one of the reasons why we might want to see if something can get a little bit more accurate a little faster, because we're going to have machine representation issues of the numbers as we go higher, or smaller numbers. Smaller numbers that we're dividing by, so they're getting huge. That makes sense? Okay. We know that, we're going to do one more thing with the error here. Remember, we know that the error is order 1, or on the order of h, which means that, again, it should be some constant times h. Now, constant is a little bit relative term because, again, when we do your Taylor series representation, remember Taylor's theorem says that the error term is equal to the derivative at some point in the interval, and then times something else, right? So that derivative that you use as you go out might change, but if we're talking about small intervals and nice functions, those numbers should be relatively close to each other, so we really do get a constant idea. So let's see if we can see that constant. So again, this should be a constant times h. whatever the H is, right? So if I divide these errors by the H value, I should see relatively the same number until things start to go haywire. Okay? So just to do that real quick, I'm going to take that C2 number and divide it by the H number. And we should see relatively constant until, like I said, things start to go haywire there at the end. Again, not quite constant, but really, really close to 0.5. Again, until we get to that 10 to the negative 8th error, the area, and then things start to go bananas. Right? So the whole reason why I'm doing this particular column again is just to show you that the error really is close to a constant times what the H value is. Dividing out the H value should make a constant number every single time, right? So it's on the order of H. If I divide out by H, then I should see constants down that column, which I essentially do, right? Plus or minus a little bit. Does that make sense? Okay. So let's do the same thing for our central difference. Remember, for your central difference formula, you're going to do f of x plus h minus f of x minus h. So what should go in the numerator here? Yeah, so exp of the h value, good. Yep. Okay. Yep, and I can type in negative a2. One thing that I discovered in Excel playing around with different things, I'm not done yet, by the way, don't hit enter. One of the things that I've done, noticed in Excel, is that if you do negative a2, it treats it all as one quantity. So if you do the negative of a2 and hit a squared, it will treat it like it needs to square the negative when it's not supposed to. Okay, so just to be safe, I do negative 1 times it in case I need to change things up later. Yes. For this one? Yeah, just give me a second to finish this one off. Yep. Okay. So this is the f of x plus h and minus the f of x minus h. Again, x is 0 here, which is why I don't need to put that in there. If we're doing this at a different point, we need to put that in there. Okay. What do we divide by for the central difference? 2h. Be careful, I do need parentheses around that whole thing, right? So 2 times the h value. Notice that right away, I've got a closer approximation, right? We'll do the same thing as we did for the other ones. I'm going to show most of the formula that's in here. There you go. That's what that one. Is that what you needed? Yes. Okay. Can you pull up the formula for simple difference? Yep. You got a parenthesis or anything? Yep, that'll do it. Okay, parentheses are kind of a pain, but necessary. All right. So again, we can pull this down, copy these down in the same places. Again, Excel thinks those numbers are pretty close to 1 the way they are. I'll spread the column out a little bit. You can see more decimal places. Again, notice that it's getting better approximations faster. Right? Don't need as small of h values to get this within whatever tolerance that you might want. Let's look at the error again. So again, I'll just do 1 minus the values that we're getting out. It really doesn't matter the order you put those in. I don't care if they're negative or positive. You can see again, every step of the way, your error is smaller. In this case, your error, in a sense, maxes out or is smallest here around that 10 to the negative fifth value rather than the 10 to the negative eighth. And you can actually, depending on the precision of your machine, you can actually come up with a formula and figure out where that max or that minimum error piece occurs. We're not going to do that, we can. I know that because I read it in another textbook, so I know that you can do it. All right. Again, that might be important for if you're doing this from a computational standpoint. You'll need to know if you're doing this for a function that you have, and you want to try to get these approximations, you might want to know, well, how far out do you need to take calculations to get to a certain precision level that you want. Accuracy level, whichever. All right. Remember again that your forward difference method, your error was on the order of h. So again, when we divide out the h, we should see a constant here, which we did, didn't it?
Oh, it's to show the side interpretation, so I can see it.
That's interesting. It was fixed on a certain number of decimal places that it was showing. So if you just go to your cell properties, or format cells, and change it over to general, I should take care of it for you. For some reason, it must have been locked into a certain number of decimal places to show, which is why you couldn't see anybody. Anybody else having that issue? Oh, that's right, your mouse doesn't work. Okay, you didn't divide, okay, so this is not the right formula. So you want to do f of x, so I do parentheses around that, and then minus the 1. Remember your formula for the derivative is f of x plus h minus f of x, and then I still have to divide by h, which is over there. Okay, and so the same thing here. This is just this divided by the h. This divided by a1. This is just C2 divided by A1. Anybody else having issues with the display? Okay. Remember your central difference formula, the error is on the order of h squared, or an order 2 approximation, right? So if I divide the error here, which is here, and divide that by your h squared, I should again see a constant all the way down, again until things start to go haywire with the error, right? So here I'm just doing the error term divided by h squared in this case. And if I copy this down, oh, for heaven's sake. If I copy this down, again, I should see the same constant, roughly, right? It's not quite constant because as you change your h, what you're using for the derivative in that Taylor's formula might be slightly different, right? But it should be close. If you got nice functions, it should be close, okay? I see constants here for the first few. Here it starts to change, and then it really goes bananas, right? But again, we can see the ratio there really does make it on that particular order. Again, the whole idea of this particular thing is the central difference formula gives you better approximations faster than the forward difference formula, and it would also work for the backwards difference formula. And you can check out different functions and see the same ideas. That's okay? All right, so we've talked about forward difference, central difference. There's lots of different other formulas that you could do. Let's do a couple of them that are in the book just to establish a couple of different things to see these. So this is number 8 on page 199. So part A asks you to show that your derivative is approximately 1 over 4h f of x plus 2h minus f of x minus 2h. And then it also wants us to establish pardon me, it also wants us to establish what the error order is. O of h to what power? So let's see if we can do this with the same kind of idea that we talked about with getting that central difference formula last time. So remember that we started with what? But how did we get this? What did we do to get the central difference formula? What did we do? Yeah, we worked with a Taylor series, right? So remember, for your Taylor series at a particular point, if I do, say, f of x plus h, that should be, well, it should be equal. You should have your f of x, and then your f prime of x times h, right? And your f double prime of x over 2 factorial h squared. I think we wrote it out before, we did an x naught, saying we would find the Taylor series expansion at a particular x naught, and then plugged in x naught plus h, right? And that's where the h's are coming from. I'm just not writing the naught, okay? Assume your x is fixed, write out your Taylor series, and then plug in x plus h. Okay. So I don't have to write x naught everywhere, is the whole reason why I'm saying that. Okay. That would be your f of x plus h, right? But this problem's not asking for an f of x plus h part. It's asking for an f of x plus 2h, right? So instead of plugging in an h here, I should probably replace all my h's with 2h, right? So let's just write that down at the next step. I just wrote that out just to remind us that was what we came up with last time. So if we do f of x plus 2h, I'd have a 2 in front of my f prime of x. We'd have a 4 in front of your, pardon me, your f double prime of x. We'd have an 8 in front of our f triple prime of x, and so on down the line. Since I'm plugging in x plus 2h, I've got to take the power on the 2 as well as the h, right? So in the first one, the first place we actually have an h, I'd have a 2h. Here I have to square the 2, or I get the 4. Here I have to cube the 2, so I get an 8, and so on down the line. What's going to change when you go from f of x plus h to f of x minus, or sorry, when you go from f of x plus 2h to f of x minus 2h? What's going to change? Yeah, which signs? The odds, right? So the f of x will be the same. The power on the derivative would change. It'll be the same on the second derivative. It'll flip on the third derivative. and so on, right? So far, so good? Remember that we want to, I mean, they already told us what formula we're trying to establish. But if we're trying to use this to get an estimate for the derivative, I basically want to solve this for the derivative, right? Oh, I forgot my h. There should be an h on that term. I'll write it down here in a second. We want to be able to solve for the derivative, right? Well, I certainly don't want to add these two things together because the derivative will cancel. So I probably want to subtract it, right? So if we subtract these twos, the two of these, okay? So we'd have f of x plus 2h minus f of x minus 2h. The f of x's cancel. Also, the f double prime x terms cancel, don't they? And then similarly, all the even ones will cancel because they have the same sign. All the odd ones would survive. Rather than trying to write these constants out every single time, we know that's a constant of some sort. So let me just write 4f prime of x times h. We'll do this minus this. There'll be some constant. I'll call it, since it's the third power, let me call it an a3h cubed. And then I would have an a5h to the fifth, and so on down the line. I'm doing this minus this, so it'll be positive. It's the only reason why I order plus. I can put a minus. It doesn't matter. It's just some constant. I'm just being lazy and not writing out what the constant actually is. Right? Okay. So some constant times h cubed, some constant times h to the fifth. And again, all the even ones cancel because they have the same signs. Okay. If we solve this now for f prime of h, or I'm sorry, f prime of x, I would divide everything by 4h, right? I would subtract all those h to the powers over to the left-hand side with a funny hand motion as I do that, right? Move it all over to the left-hand side, divide by 4h, right? So we'd have 1 over 4h times that f of x plus 2h minus f of x minus 2h. And then we'd have a bunch of things with a minus signs, right? I have a minus a3h squared, an a5h to the fourth, and so on. And the signs are all flipped because we moved it to the other side. Here's our formula in terms of our original function, and what's left on the end has all of these powers of h in it. So again, if we truncate, if we just drop off the end, there's our error term. What's it on the order of? H squared. It's in order 2. Yeah, good. So this is what it means by establish that result. Here's our derivative approximation. This is the O of h squared part. The error is on the order of h squared in that case. Yeah, lady?
How come in the last equation, how come it's like a sub 3h squared when and the one above it is a sub 3h cubed?
We divided by h. We divided both sides by the h.
Okay.
So it cancels an h out in each of those. Technically, I should probably have an a3 over 4, but it's just some constant, so I didn't, right? Because I also divided by 4. I'm solving for f prime. I'm dividing by 4 to the h, right? So, how? I'm trying to solve for a for f prime. I got to divide by the constant that's multiplied by it. So I'm dividing both sides by it. That's where this over 4h came from, too. Yeah. So, technically, if I want to be really hyper technical, but again, these are just some constants. I don't care what they are. There really should have been a 4 here and a 4 here, right? But as far as I'm concerned, they're just constants. If I divide it by a 4, it's still a constant. It doesn't matter. Because remember when we're doing our big O notation, we're just saying it's some constant times that power, right? right? We don't care what the actual constant is. Seems like we should do another one. I'm feeling like we should do another one. I don't think you're feeling any of it. Okay, good enough. Let's do another one. This is part B. Part B of the same problem asks you to establish a formula for approximating a second derivative. So it wants us to establish the formula that the second derivative is approximately 1 over 4h squared, and then times the sum that we have there in the brackets, the f of x plus 2h minus 2f of x plus f of x minus 2h. Notice when we're establishing these formulas for estimating these other quantities, pardon me, we're trying to establish these in terms of the function because that's what we're given, right? We don't want to try to establish these necessarily unless you're going to start doing things recursively. We don't want to try to establish these things in terms of the function and some of its derivatives unless we're going to estimate the derivatives as we go along, right? The things that you would be given if you're collecting data are the function values, and you're trying to approximate things based on the function values you're given, right? We're not necessarily given an explicit formula for a function, necessarily. So that's why we're trying to go back to the original and get these estimates that are back in terms of the original function. Because you're going to imagine that you're given a table of values and asked to approximate a quantity based on the table you're given. All right. However, you kind of do see a derivative piece in there, don't you? That was just in the previous part. I see this f of x plus 2h. I see an f of x minus 2h. I see a 1 over 4h out there. It's not subtracted anymore, but I really do see kind of that derivative piece that's in there. All right, but we're going to use the same principle. We're going to combine our Taylor series in a particular way and then solve for what we want, right? Well, in the previous step, we already wrote out our Taylor series for f of x plus 2h. Oops, it's 2 plus 9. Just rewriting the same thing we came up with before. And you already told me last time that when we changed the minus sign, or changed the plus sign to a minus sign in the middle there, it just flipped all the signs of the odd powers of h. Right? You agree? Okay. All right, so we're trying to solve for the second derivative now, right? Trying to solve for the second derivative now. Pardon me. If I want to try to solve for the second derivative in terms of the original function, and I don't want the derivative involved, right? I'm trying to get rid of the derivative part. Yeah? Okay. So what should I do to those two pieces so that I can solve for the second derivative but get rid of the first derivative? Just add them, right? The first derivative terms there have opposite signs. So I can just add the two pieces together. If you do f of x plus 2h plus f of x minus 2h, notice you'll get 2f of x, right? Because you'll add the f of x's together. Your odd terms cancel. Odd powered h terms cancel. If I do a little bit of simplifying here, 2 factorial is 2. So I get 2 as a coefficient here on the top one, and a 2 as a coefficient here on the bottom one. So we get 4f double prime of x h squared. What happens in the next term? They cancel, right? They have opposite signs again. Yeah. Okay. The next one will have some constant. I'll call it a again. I'll use a 4 since it's the fourth power. I'll have some constant h to the fourth. The fifth power terms will cancel again because the odd ones are going to cancel. They'll have opposite signs. So then I would have an a6, h to the sixth, and so on down the line. Yeah. Now what should we do? We're trying to get an approximation for the second derivative. What should we do? Yeah. Subtract everything over and divide by 4h squared, right? So you'll get the second derivative will be 1 over 4h squared times the piece that we need. Hey. These will all get subtracted, and we're dividing by 4h squared. I'll put the 4 in there this time. I don't want to be... Doesn't matter if the 4 is in there or not. It's just a constant. A4 over 4 times the h squared, because again, now we're dividing by h squared, right? A6 over 4, h to the fourth, and so on down the line. Yes. Oh, those are minuses. Yep, sorry. I'm subtracting. You're right. You're right. They're minuses. Thank you. So again, now we can see our approximation formula here. Here's the approximation formula. This would be the part we would truncate. That would be the error part. It should be a6 over 4 because we're dividing both sides by 4. We're dividing by the 4h squared, so it should be a 4 on bottom. Yeah. Again, doesn't matter. It just needs to be a constant. So again, we're truncating. What's the error to then term going to be on the order of? Yeah, 2 again. It's h squared. Yeah, exactly. So we see O of h squared again. That's okay? Yes, that one.
Why are we subtracting the a4 from these?
Why are we subtracting? Because I'm trying to solve for this term. So this whole thing needs to get go to the other side. Yeah. They all get shifted. Is that right? Okay. Notice that everything that we've come across so far has been on the order of h squared that we've done, right? It'd be nice if we could get our error term to be on the order of something even a higher power of h. It means it would converge even faster. Okay. So this is where Richardson's extrapolation is going to come in. All right. So let's say that we've got some quantity, and since I'm talking about some quantity, I'll denote it by Q. Whatever that quantity happens to be, let's suppose that we have this approximated by some function of our h. And then let's say that it's an order n approximation. So then I know that I've got some constant times h to the n as our order n approximation. And then something on the end that could be on higher orders of h. So I'll just say O of h n plus 1 on the end. Okay. So again, just to go through the different pieces, I know I just switched to a whole bunch of letters on you. Okay. Let me scroll down this way. Get this on the same page. Looking at what we just came up with. The second derivative here would be your Q. This part right here would be your f of h. This part is that kh to the n, the constant times some h to the power. That's the thing we were saying was the order n approximation. In that previous derivation we just did, it was an order 2 approximation, right? The rest of this is on the order of, well, it's technically h to the fourth, but if it's on the order of h to the fourth, it's also on the order of h cubed. So I've just broken that up into 3 pieces. Okay? All right. So here's how the extrapolation process works. The whole idea of this extrapolation is I want to kill off this h to the n term. I want it to go away. I want to get a new approximation based on the old approximation that has a smaller error term. Smaller error term means it converges faster, right? So this is the idea of the extrapolation. I want to get rid of this thing based on a different estimate, okay? Now again, remember, f of h is an estimate for q, but this h could change. No matter what h I use, it gives me an estimate for q, right? This formula is still true. So what we're going to do is we're going to replace the h with h over 2. Okay? That still should give me an approximation for the q. This should be f of h over 2 plus k times h over 2 to the n. And this has still got some error term that has n plus 1 terms in it. Yes?
Can you explain why we're dividing this two?
We're just trying to get another approximation of the quantity, and we're using a smaller value of h to do it. If I replace the h to the n plus 1 with an h over 2, it's still going to just have constants in it. So it's still on the order of h to the n. The 2 to the n will come out in front of it, so you'd have a 1 over 2 to the n times an h to the n, or sorry, 1 over 2 to the n plus 1 times an h to the n plus 1. That's still a constant times the h to the n plus 1, whatever the n is. So it's still on that same order, so I don't have to worry about that piece. Good question. Why didn't I replace it? That's why I didn't replace it. Yeah, because it's still a constant there. Good. All right. So again, the whole idea of this, I'm trying. One of the reasons why by the way, the h over 2 doesn't really matter as long as you do it by something smaller. We'll just use a 2 because we can have things pretty quickly. I could have done 3s or 4s or what have you. We just needed something smaller. Is the idea. Now, I will mention before I keep going. Notice that this extrapolation process is much better if you're given an explicit formula than if you have a table of values. Because at some point when you have a table of values, you don't know what's in between. Now, that being said, if you have a table of values and you've got some function that you've used to approximate through that table of values, say through polynomial interpolation, then you can do something like this. Okay? All right, anyway. Plugged in h over 2 for h. This is still on the order of h to the n plus 1, so I'm not worried about what the constant is. Okay? All I'm worried about is trying to get rid of this term. That's all I care about. Okay? This is going to be 2 to the n that we can pull out in front. So I'll just rewrite this as f of h over 2 plus 1 over 2 to the n k times, h to the n plus O of h to the n plus 1. I just pulled the 2 to the n out. Okay. All right, so I'm looking at, so I'm going to do this in a different color here. Here is one approximation for Q. here is another approximation for Q. And I said that I want to get rid of the h to the n term. So much like what we were doing in the previous couple of examples and what we did last time, what can if I think of these as equations, as a matter of fact, if I have it written this way, it probably is an equation, rather than approximately equal to sign, but again, we're thinking about approximating the f of h, and in a lot of things, we don't know necessarily the k doesn't change depending on the value. They should be close. Anyway, what we were doing in the last couple of things, if I want to try to get rid of this k h to the n term, what can I do with these two equations? Yeah, I need to subtract, but I'm going to need to do something to one of them before I subtract to make it go away. I agree, we'll want to subtract something, but I need to do something to one of them. Yeah, I need to multiply the second one by 2 to the n and subtract, all right? Because I need to get this to go away. So I'll have a 2 to the n q, I'll subtract up, just so that things are positive. We'll have a, change back to black here, 2 to the n q minus q. That'll be 2 to the n f of h over 2 minus f of h. Right? 2 to the n times the bottom one, add up. These, again, I don't know what the constants are here, but I know that they're both on the order of h to the n plus 1. I certainly don't add an h to the n in there, right? It's possible the h to the n plus 1s go away. I don't know that they do because I don't know the constants are the same, right? But I do know that the order didn't decrease, right? I didn't go from h to the n plus 1 to some other smaller power of h. Right? I didn't magically add an h to the n in there. It's possible the h to the n plus 1s went away, but I didn't magically put a smaller power of h in there. It might have gotten higher, but it didn't get lower. That's all I'm saying there. Okay. Can we solve this for q? Yeah. I'd have 2 to the n f of h over 2 minus f of h all over 2 to the n minus 1. And then, I really probably should be using equal signs on the end, but it doesn't matter. Again, here I'm dividing by a constant, so this is still on the order of h to the n plus 1. Now, from an old approximation of order n, I've created a new approximation of order at most, or at least, I should say, n plus 1. Might even be better, but it's certainly it might even be better than n plus 1, but it's certainly better than n, right? Okay. I can rewrite this and kind of give a word description of this approximation. It might help a little bit. Let's add and subtract f of h over 2 on the top. So I'll do minus f of h over 2 plus f of h over 2. Oops. The only reason why I'm doing this is that I want to try to get a little bit of a word description of what's going on, and then we can start doing a couple of computations as we go along. Okay? I'm going to split this fraction at the plus sign here, right directly in the middle. On the first one, we can factor out an f of h over 2 out of both terms. What are you left with when you factor out an f of h over 2 in both terms? 2 to the n plus 1. So you're 2 to the n minus, or 2 to the n minus 1, so those will cancel, right? So this will be equal to f of h over 2, and then I'll write it as plus 1 over 2 to the n minus 1 times f of h over 2 minus f of h. In words, what have we done here? This is old estimate. This is new estimate, right? In some words, this is less accurate, more accurate, right? So your Q, the approximation here, is the more accurate, plus 1 over 2 to the n minus 1 times more accurate. Room on the side here, minus the less accurate. Yes. This part? Okay. We're going to split it at the plus sign. Factor out f of h over 2. You're left with 2 to the n minus 1. So those will cancel in the first term. And then the other term is what's left. Split this right directly in two. Would be this over this plus this over this. The second part is just that over that, right? In the first part, your 2 to the n minus 1s will cancel after you factor out f of h over 2. All right. Notice that your n here is what? What did the n refer to? Yeah, the original order of the approximation, right? So this has an order at least n plus 1. If you want to do it again, it's the same formula, except that this is going to get even bigger, depending on what the order of the approximation is. Okay? So let's do a specific example of the central difference formula that we talked about for the derivatives, and then plug in some numbers and see if we get an approximation. That's the whole point of this, right? Okay. So let's go back to our central difference approximation. Remember that when we did our central difference, we had f of x plus h minus f of x minus h over 2h, right? This would be this is what we're calling capital F of h at this point now, right? What order approximation did that have? It was 2, right? That is h squared, right? But also remember that when we did that order 2, remember the reason why it was order 2 is because we had some constant times h squared. What was the next term in the approximation? It wasn't h cubed, it was h to the 4th, right? So if you go through this approximation formula, when you go through the extrapolation and get the new estimate, the more accurate estimate from the older one, you're going to get an order 4 approximation rather than an order 2. Do it again, you'll get an order 6. Do it again, you'll get order 8. And you can keep getting better and better through the extrapolation. Okay. The reason why we need to keep track of that is because we're going to divide by that order, right? So it's important to keep track as you're going along for what your order approximation is. So let's just play around with why that would be true in this case. So let's see if we can redo this. We had the f of x plus h was, let's just write it this way. That was our f prime of x, and then it was plus some constants times h squared, and an h to the 4th, and h to the 6th, and so on down the line, right? That was what we got to. Okay. So, pardon me. Notice that your formula says to do what? It says to replace the h with the h over 2 and see what happens, right? Rather than writing this thing out over and over again with the 2h in it, or with this formula. Again, let me call this the f of h piece that we're trying to use to approximate it, right? Then your f of h over 2 will be what? Well, it's still f prime of x, because that part doesn't change, does it? Okay. This part becomes, I got to square the 2 that's on bottom, right? So you'd have 1/4 a2h squared. The next one would be 1/16 a4 h to the 4th, and the next one would be 1/64 a to the 6th, h to the 6th, and so on. Right? Okay. So just doing this in this specific example for this formula, notice that I can do the exact same thing that I talked about generally, but let's do it with these specific numbers. I want the h squared term to go away. How do I make the h squared term go away between these two equations? Yeah, subtract them. I need to do something with this one again first. Multiply by 4, right? Okay. Multiply the second equation by 4 and subtract this first equation. You'll get 4 f of h over 2 minus f of h. Right? Okay. This is what? 4 times that minus that will give me 3 f prime of x. Right? We agree with that? Right? 4 times that minus 1 of those is 3 of them. Right? These go away. 4 times, these are just constants, right? Okay, so I'm just going to write them as constants. I'll just say a b4 h to the 4th, a b6 h to the 6th, and so on. Right? I don't care what the numbers are. I just care that they're constants, right? So I just rename them. I don't feel like writing them all out. No one cares what they are. Okay. All right. Again, now if we solve for the f prime, we would divide by 3. Yeah. So you would have 4 f of h over 2 minus f of h all over 3 gives you an approximation for your derivative, and this is order 4 now instead of order 2. So your order 1 got that, right? Yeah. And like we talked about before, I could put a minus and a plus this term, right? And you would have the 3's would cancel. And then you would have 1 over 2 to the n, 2 to the 2 squared minus 1. And then times the new minus the old in there. This is an order 4 approximation. So if you wanted to go from this one to the next one, notice that all the even terms are all that are left. So now if I go off of this as my new f of h and do the exact same thing again, I can get an order 6 approximation using the same formula off the old one. If I do it again, we can get order 8 and keep going. Okay? This is the extrapolation process. Okay? Of course, we have to divide our h in 2 each time to be able to do that. But this is how the extrapolation works. So let's see if we can't apply this to a specific one. Maybe. All right. So let's take a function. Let's say we did, let's write this on the board. Let's do something that we know so that we can check it pretty quickly and not have to do a nasty derivative formula to it. So let's say sine. Okay. Let's say we do sine. We know that, let's say we want to use this extrapolation process to estimate f prime of 0. But again, we know what that answer is. Derivative of that sine is cosine, and then cosine of 0 is 1, right? So we should be getting 1 for our approximation, or at least something close to 1, right? All right. So again, we need to start with h's that are going to be approaching 0, right? So let's start with, I don't know, 1. Start there, and then have it each time, okay? All right, so we'll do 1, and then again, we'll have this each time. So I'll just have these to reference to. Oops. So remember, each step in the extrapolation will have it. I'm not going to go down too many terms here. All right. Actually, I probably should have put another column there to don't make sure that we knew what order we were at. Actually, let me do that. Move this over a column so that we can see that. Just take this whole thing and move it over a column. All right. We're going to start with the order 2 approximation at 1. When we have it, we'll get an order 4. Have it again, we'll get order 6. Have it again, we'll get order 8. All right? We agree? Okay. All right. So let's work off of this one. Again, central difference formula. Is that one, the f of x plus h minus f of x minus h all over 2h. That's central difference formula, right? Okay. So we want to work off of, I guess I'll go over this one. We want to work off that one to get the new one, right? Okay. So if we do the central difference formula here, your numerator would be sine of x plus h, but again, we're using x to be 0. So it's just sine of the h value, right? You agree? And then minus sine of negative the h value. And then divide that by 2 times the h value. Go back in there so you can see the formula. Sine of the h value minus sine of negative the h value divided by 2 times the h value. That's the central difference approximation using the h value, right? Okay. This okay? All right, so I'm going to copy that down. And we do see that these are approaching 1, but not particularly quickly, right? All right, so let's see if we can go to an order 2, going from order 2 to order 4. So this is order, I guess maybe I should have labeled my 2 here and cross this way. Doesn't matter. Okay. I want to go from order 2 to order 4. So I'm going to work off of these 2 to get a new approximation because this is half of this. But I can also get an order 4 approximation by using these 2 because this is half of this. And same way here, right? Okay. Yeah, I mean, I guess I probably really should have put my labels across the top rather than down the column, but we'll figure it out. Okay. All right. So how did we get this? Remember, it's new plus 1 over 2 to the n minus 1 times new minus old. Right? Okay. So it's new, which is this one, right? Plus 1 over, 2 to the order. It was order, the old order is 2, right? This is why I should have put it in that column. I'm going to copy here in a second. I'm going to do an absolute cell reference here so it doesn't change. Well, maybe I'm going to do an absolute cell reference. It just disappeared. That was weird. F4. There it goes. This computer has been crazy today. It's 2 to the order minus 1, right? Okay. And then times new minus old, right? Okay. And then copy. Look at how close, look how much better those approximations are based on the old ones. Right? Now we have order 4. I am going to put these across the top so we can actually see them. This is order 2. This is order 4. Next column here we'll do order 6. Okay? I can use these two now to get an order 6 approximation, and I can use these two to get an order 6 approximation. Same exact formula, I just got to change what the order is, right? So let me go, I'll do this probably a little bit more easily. I'm going to take this and copy it over. Now I do have to change the order. And instead of A16, I want A17 because that's the new order. Because those are order 4 approximations. But the formula is exactly the same. It's, I'll hit enter and put it back in here again. It's new plus 1 over 2 to the order minus 1 times new minus old. All I did was just go in and edit the formula and change what the order was. That's all I did. Just went in and changed what the order was. Okay. So far, so good? Okay. Yeah. Yep. Oh, I'm out of time. Holy crap. Let me just finish this off real quick, and then if you got questions, we can talk about it. But me, since I'm out of time, I didn't realize it was already 10:46. Sorry about that. Copy that down. Look how close they are to 1. Right? Look at what your H value is. That doesn't even take a very small step. Right? We just halved each time. I've got an H value. I've moved a whole 1/8 of a unit away from 0. Right? That's a pretty big step. But I've got a really accurate approximation of the derivative. Right? That's why this is a big deal and why this is a nice way to do this. Because again, I don't have to use really, really small numbers, which your machine has a hard time dealing with when it divides by small things, right? Okay? And I can get really, really accurate approximations without having to divide by really, really small things. That's the whole point. All right? We'll do a couple more examples of this next time. We will have a test next Thursday. All right, so we'll talk about that on Tuesday. That'll be what Tuesday is devoted to. Is that like a plan? All right. Have a good one. Sorry to keep you a couple minutes late. Apologies. You can downgrade me on my evaluation at the end of the semester. Totally worried about it.
I'm gonna overclass one day.
I can't believe him.